Greetings, loved ones. This is your captain speaking. Welcome, everybody, to the Hot Pet session on new avenues in privacy. Coming up first, Jack is going to tell us about research opportunities in I2P. Let's give him a hand.
Thank you. I hope everyone enjoyed the ice cream break. I thought it was quite nice actually being just afterwards because it's kind of a cultural dish in New Zealand. And I now have something to sort of spruce you up at the end of what has been a very long and eventful week. So, thought I don't think I need to explain what Tor is at this point for context, but I thought I'd give a little brief overview for those who aren't aware of what I2P is. If I were going for the single sentence version, it's that, low latency onion routing location anonymity network, hence I needed the wide slides. For Nick's benefit, here's a call diagram, call flow chart. It's just for the I2P main library binary. There's a bunch of other stuff in there, but basically it's a onion routing network where everyone, star, is a router, depending NAT access and such. The routing info is stored in a DHT and distributed by flooding, as a variant of Kademlia DHT. Tunnels are unidirectional, which is sort of one of the key things that is mentioned as a difference, and I will get into that more later. And I've got a bunch of reference implementations there. So if you think Java's ew, you can go for C++. If you think that's ew, then go, or, yeah. Just for a bit of context for what I'm going to talk about, this is what I call the I2P layer cake. It's reasonably well stratified, some nice deliciousness in there. You can basically see three sort of layers of arrows there that I might refer to later. Bottom layer is our link layer, crypto. Middle layer is doesn't really show it too well, but it's the onion routing-esque layer, and then there's an end-to-end crypto layer on the top. So, when it comes to literature about I2P, we actually have a not insignificant amount of work that has been done before. Most of it sort of started around 2009, people taking interest in reviewing it, and spread across a reasonably wide variety of areas. We also have a rather ancient design document from 2003, which doesn't really give much information because they still hadn't finished designing it at the time. What we really have now is a living specification. So if you ever wanted to implement a router, you go there, and it should be sufficient for you to implement from scratch. We know this because those other implementations have bug tested it. But there is still plenty of scope for research available within, I'm sure that there were some weird synthetic biology results that were coming out of these, but for the most part, it's somewhat indicative of the fact that there's a lot of scope available here. And in particular, I'd like to touch on three things that I feel are reasonably understudied or not really answered at all in the literature, which is A, the use of, utilizing the fact I2P's packet switch nature in, for more fun routing, the use of peer profiles, which I'll get to in a moment, and then the trade-offs of unidirectional tunnels. If you're interested in anything else, I have a literally laundry list of to-do lists items for research, so you feel free to ask me about anything later. So, getting back to this layer cake, the way that we have it implemented, the base link layer runs over TCP or UDP, but pretty much everything above that is packets. And in particular, we have two areas, firstly at point A, at the end of a tunnel, and secondly at the end-to-end point, where you can specify routing information independently for every single packet. So what this means, apologies for the graphic, it's from 2005, when Alice wants to send something to Bob and Dave, she can independently route each of her packets. Now, at the moment, we tend to do things relatively simply because, you route, if you make a connection, you route it through a single tunnel, but you can have multiple tunnels available. And so it is possible to do fun things like multipath TCP, where you split up packets across multiple tunnels for performance reasons, or and also potentially for privacy benefits, splitting the traffic signals across multiple tunnels to reduce what a single adversary may observe. And then additionally, we can do fun things like one-to-many broadcasts for efficiency. This latter is actually somewhat implemented at the moment, But there's far more we could do, like the multipath, as I mentioned, that isn't really being done at all, and hasn't really been studied in I2P's context, at least. So if people are interested in that, then that's one fun thing that would be fun to do. Very fun, yes. The next bit that I want to touch on is the peer profiles, and so I have to mention the network database. So in a system where you have directory authorities like Tor or a mixednet system or something, the network peers will publish their information to the directory authorities, who can then create essentially a view of the network that then gets published down to the network peers. And so any peer can go, yep, I know this network, I trust these authorities or this collective of authorities to make decisions about bandwidth weights and some such, and so I can use that to make my routing decisions. If you don't have a directory authority, things are a little bit harder. So you obviously can't scrape that information from anywhere in particular. So a lot of it has to be, we use a DHT, so it has to be distributed in band between participants. And of course, you have the opportunity to lie in the DHT. There's bounds on that, of course. So a member a participant in the network obviously has to prove that they publish some bit of information because it has to be signed. But what is put into that, what we call a router info, the information about that router, could be entirely false. So you could be advertising capacity you don't have. You could be lying about your IP addresses and using other people's IP addresses for things. So there's a bunch of stuff that obviously needs to be done if we're going to use this information safely, because we have to start from the point of all information in the DHT being untrusted. And so what we do is I2P builds up these peer profiles. And the way we do this is whenever we are building tunnels through our peers, we collect metrics. So, for example, the speed metric will be how fast we find tunnels that are built through that particular peer. Capacity is generally done on a metric of how easily we can build tunnels through that peer. So, say to give an example, if you're able to build 10 out of 10 tunnels when you try with a particular peer, that's better than if you could build 10 out of 100, because they're obviously dropping, or that peer or some other peer may be dropping 90% of the packets through that. So we build up these profiles in a way, and then for the purpose of peer selection, we break it down firstly into, can I reach this node? Kind of helpful. Then in the current I2P implementation, we then first sub-select by the high capacity nodes, so nodes that have some chance of being able to build a tunnel through. And then we sub-select from that for the peers that we observe to be fast. And that is the subset of peers that a router knows about that we choose to build our tunnels through. Now, of course, a lot of this matters on how we do these metrics and how well they can be gamed, how well people can pretend. One example of something that matters, a tunnel has multiple participants. How do you know when a tunnel fails which participant had a problem? So what we generally do is we apply a negative weighting to all of the participants in a tunnel loop, for example, weighted by where it's more likely to have had a problem. So for instance, when you're sending tunnel packets along a tunnel, the packets themselves will be smaller in the tunnel than when it gets to the end, because we have fixed-size tunnel packets. So you could be sending a 16 kilobyte packet through a tunnel, and it's far more likely to be dropped once it gets out of the tunnel than somewhere along the way. So we can do metrics like that, but how we do these hasn't been particularly well studied. And there are many other metrics that we could be going on. This is what the peer profile, and a snapshot of the peer profiles on one of my routers at the moment. We collect a bunch of metrics about these, and it would be really nice to know if any of this other information could be useful to try and give us a leg up in terms of how we select our routers for, I've got to do this right, how we select our routers for tunnel building. And then we get to the fun one, unidirectional tunnels. So this is the biggest design difference between, say, I2P and Tor. When you go to connect with a peer, in Tor, obviously, you build a circuit, and then you send data to your peer, your hidden service or whatever, through that circuit, and then data for the return path comes back through there. So if you're a middle relay or an exit node or whatever, you can sit there and see, oh, data's going that way, data's going that way. I can work out who the client is, who the server is, and do packet counting on the request and response. The original idea of I2P going for unidirectional tunneling was that unidirectional tunnels was that it cut out half of that information. So you as a participant, say J, you only ever see packets going in one direction. So it, in theory, becomes much harder to work out if you are on an inbound tunnel or an outbound tunnel, whether you are part of a rarely used HTTP connection or potentially a spottily used download. Or the idea is that because you only have one pathway, you have to do a lot more work to figure out what's going on in the tunnel. There has not been any full study of this. The closest that we have in the literature was a study that was published in PETS 2011, actually, it was presented here, where they did a basic mathematical analysis of peer selection and going the probabilities of if you have a set of size S and you have a number of attackers A in that set, what's the likelihood of picking one of those enough of those adversary pairs that you get a pair on either side of the client. So a client has inbound tunnel, outbound tunnel, and you're looking to get pairs right there. Their conclusion was that unidirectional tunnels meant that it was harder to get to that position, but once you got there, you were more certain. And they claimed an S-squared improvement on false positives. Now, whether or not this happened to be accurate at the time, which I do have a few reservations about, it certainly doesn't cover what we now do in terms of the way in which we perform peer selection. And so what is really missing in this space is an in-depth look at the trade-offs of unidirectional versus bidirectional tunnels. Like I said, the original design intent for unidirectional tunnels served one purpose, but then the Herman analysis found a slightly different style of timing attack that it was vulnerable to. So maybe that means that unidirectional tunnels aren't a good idea. But there are other, it depends on a certain certainty versus time trade-off that may not be the case for certain adversaries, or maybe any adversaries. And in particular, this ties back into the DHT issue because peer selection matters. And for example, one of the things that we do is we enforce strict ordering of pairs. So when we picked those 3 pairs or whatever for a tunnel, they are ordered based on their XOR distance to a random key that is picked per inbound and outbound tunnel, which was intentionally designed to combat the predecessor attack where you look at the pair that's just before you or the pair just after you. So is that sufficient to survive this? Are there other things that we can do to improve this? Or is it just hopeless? So there isn't any academic or research guidance as to that trade-off, and in particular how then the peer profile stuff could potentially influence the success or failure of this strategy. So yes, a full analysis of this kind of thing would be really, really lovely, and I think could be quite beneficial from a research point of view, because it's not something that I have been able to determine has been studied before. So yeah. Basically, I'm going to finish up with my questions here is, firstly, how useful is all this? If someone were to say, oh, yeah, there's this paper that was published back in 2001, and it covers the exact use case, and it's not going to work at all. Great, please tell me. I would love to know about that paper. But also in particular, assuming that's not the case, and there is still some usefulness here, how can we make I2P more amenable to analysis for researchers? There's the talk earlier today about a wide area testbed for Tor. Would researchers prefer something similar for I2P? I've had multiple people tell me, you need to write a design document. I think I'm going to be spending the next 5 months of Fridays doing that, possibly. But yeah, and then how better can we as a community engage with the research community to better enable you to do these sorts of studies and better enable you to get access to the information that you need. There was going to be a mailing list URL there, but I haven't actually set it up yet. I meant to take that out. Apologies. I'd hoped to sort of mind capture you while you're all here, but apparently Mailman 3 is a little hard to set up. So with that, I will leave it there. Look forward to your questions. Thank you for your time, and ice cream.